a little more about curves in space. Now here we have a curve in space with some points denoted in red, and from some of those points we have vectors traveling along the curve. These are velocity vectors. Notice that if you look at the scale, these are not unit vectors. So if they are velocity vectors, they not only show the direction in which the particle or the object is moving, but the length of these velocity vectors denotes the speed at which the particle is moving at each point. Now, the following information I'm using in this video and the GIFs, the animations, were posted on a Google Math group in August of 2015, and I thought the animations were just really cool, and so I've incorporated them into a video. And here is the website address in case you wanted to go check it out. So we're going to start with what was posted by this particular person who calls himself Math. Graphs of the tangent, normal, and binormal vectors for a parametrically defined curve is what we're going to be discussing here. Now we have a curve in space, and at any given point you can define 3 orthogonal vectors with respect to the curve. Orthogonal meaning they're all perpendicular to each other. The first is tangent to the curve. It points along the curve. So let's take a look at that. It's pointing along the curve, and notice it's always the same length. It's always 1 unit, and so what you do is you take the velocity vector and divide by its length and create a unit vector in the direction of velocity, and that's called the tangent vector. The second vector is the normal vector, which points in the direction of greatest curvature. So let's take a look at that. And again, it's 1 unit long. And the third is the binormal, which is perpendicular to the first 2. In terms of physics concepts, if you think of the space curve as the path along which an object is traveling, the tangent vector is in the direction of its velocity and tangential acceleration, and the normal vector is in the direction of its centripetal acceleration. The binormal vector then is equal to vector t cross vector n. Now this notation is a little strange. Mr. Math must be from Europe or some other country. This is the way we would write it. T of t cross n of t. Now that's a good way to describe a curve in space, and we need all 3 quantities to do a good job. So let's take a look at all 3 vectors put together. The blue one is the tangent vector, the red one is the normal vector, and the green one is the binormal. Now notice that the binormal is also a unit vector because remember that the length of a vector that's the cross of 2 other vectors is equal to the area created by the 2 original vectors. And since they're unit vectors that are perpendicular, that's a square of unit 1. And so the green vector, the binormal vector, is also a unit vector. The unit tangent vectors are graphically intuitive because we're used to thinking about tangent lines of curves in single variable calculus. Now the normal vector points inward as seen in the following animation. We didn't really specify that before, but inward would be towards the greatest curvature. So let's just take a look at that animation one more time and notice that the normal vector always points inward. Now what you can do is you can think of a circle that's tangent to the curve at any given point, and then the normal vector points into that circle. Now the curvier the curve is, the more curvature it has, then the smaller the circle. So see up here where it's real curvy, the circle is smaller. And in fact, the radius of the circle then is small when the curvature is large and large when the curvature is small. And in fact, the radius of this tangent circle is equal to the reciprocal of the curvature. And finally, the binormal vector is b equal t cross n. And again, that notation is a little wonky for us. We would write it this way. Now, there's one more vector we need to talk about, and that's r of t. If you'll remember, r of t is the vector that defines the curve in the first place. It's drawn from the origin up to the curve. So r of t is called a vector valued function, where t is the independent variable, a real number, and at various t values, which you can sometimes think of as time, r of t takes on a different value, a different vector. And as t varies, r varies, and draw its tip. When you draw it from the origin to the curve, its tip traces out the curve. So let's take a look at that. Here's the three vectors again. The blue one is your tangent vector, the red one's your normal vector, and the green one's the binormal. And now r at different values of t is going to point to the curve from the origin. So there's one for a small value of t. And again, we're moving, as t moves in the positive direction, r of t moves in the same direction as the velocity vector. So there's another r at a larger value of t, and another r at an even bigger value of t, and another one, and another one. And the velocity vector then, if you take the derivative of r of t, you get v of t, which is also a vector valued function. And when you plug in values for t, then you get the individual velocity vectors at each point. Okay, so now I'm going to leave you to do some problems on your own, and look at my other videos so that you know how to do the problems and the calculations. And I will leave you now with some music. Ta-ta!